Welcome to EV Society's Canada Talks Electric Cars webinar, and thanks for tuning in to our 34th episode. Hydrogen and its viability in transportation, as well as other sustainable energy applications, continues to be a topic of debate. Hydrogen proponents tout the fact that it burns without producing any CO2 or pollution, and is one of the most abundant elements in the universe. Its detractors point out that hydrogen does not exist in a pure state and must first be extracted from its source and converted into a usable form. Costs and inefficiencies surrounding this extraction process are among the reasons hydrogen has yet to play any significant role in sustainable transportation. Despite the debate, vast sums of money, mostly tax dollars, are being provided to fund research and hydrogen projects here in Canada and around the world. Today, we explore the challenges of using hydrogen as a fuel in vehicles and other applications. Jason Arnaud will curate your questions and present them to our guest speaker at the end of the talk. Please add your questions to the Q&A window at any time. I'm pleased to introduce today's guest, Mr. Paul Martin. Paul is a Canadian chemical engineer with decades of experience making and using hydrogen and synthetic gas. His keen interest in electric vehicles and the electric transition has been earned honestly. He converted a 1975 Triumph Spitfire to fully electric in 2014. And then he did the same in 2020 with a 1973 TR6. Paul is a chemical process development specialist offering services to an international clientele via his private consultancy, Spitfire Research. Paul is also a co-founder of the Hydrogen Science Coalition, a nonprofit organization providing science-based information about hydrogen from a position free from commercial interests. So on that note, Paul, welcome to Canada Talks Electric Cars webinar.
Hi, and thank you very much for having me. I'm looking forward to giving the talk today.
Absolutely. Well, there's a lot of interest. We have folks tuning in tonight from, of course, across Canada, but in the United States and outside of Canada as well. So it's a topic that's certainly of great interest, and we look forward to hearing what you have to say. I'm going to get out of the way, Paul, and let you have at it.
All right. Well, great. Thanks again for everyone attending. So what we're going to talk about, well, first, I'd just like to introduce myself. I've been introduced, I think, quite well, so I don't have to add too much. You can see me there with the gas tank out of my 1975 Triumph Spitfire. And if my video image is up, you'll see the hood of that Spitfire hanging on the wall there. I have been working with hydrogen since my undergraduate, and I've got quite a bit of gray hair, so you know that was quite a while ago. And ever since then, on project after project, making and using hydrogen and synthesis gas, which is hydrogen mixed with carbon monoxide. And I've been a former fan of hydrogen and using hydrogen as an energy vector. But when I got involved in it in a deep way on several projects that involved developing and helping a client patent technology in the area, I came to realize exactly what its fundamental limitations were and that we weren't going to get around those. And so that's formed the basis of a lot of public commentary in the past while, and in fact led me to co-found an organization called the Hydrogen Science Coalition, which consists of people like myself, or largely retired engineers, academics, and others who have no vested interest in relation to hydrogen, but the knowledge to be able to communicate on it effectively and to provide a science rather than an economic-based opinion about the matter. And as I mentioned, of interest to this group, I did this EV conversion with my son in 2014 as both a learning exercise for myself and my son, and also as a way to decarbonize my commute. I had quite a long commute at the time, driving between Toronto and Burlington and back every day. And so here are a few pictures from that conversion. This car, I bought this car back in university, and it was in pretty rough shape. So there was a lot of attempting to correct metastatic car cancer on this thing. That took a lot of time, but it was the car I had, of course, and I loved the thing. And I did a pretty simple AC conversion with lithium iron phosphate batteries. There's my son Jacob wiring up the battery pack. And I drove that car back and forth to Burlington, spring through fall, for 4 years, and loved every minute of it. But one day in July of 2018, I was driving home. I was on Highway 401, and somebody with a big Dodge 2500 pickup truck with dual rear wheels didn't notice this silent little orange car driving next to him, and changed lanes into me, and destroyed hundreds of hours of effort. As you can see there, I was lucky to be uninjured. In fact, I was probably lucky to be alive after that collision. But the good news is all the electric stuff came through the crash just fine. And after a period of time wrangling with insurance companies and dealing with other issues, I finally got around to converting another car, just dropping that drivetrain into this 1973 TR6 that I bought with no intention to convert it. And that car is out in the garage, needing a battery pack balance and a few other little twitches in order to get it ready for the spring, but I'm very much looking forward to driving it again. But today our primary interest here is going to be to talk about hydrogen, what it is and what it isn't, especially in the context of decarbonization. And so what you hear in the media and from the mouths of a lot of interested parties is that, it's the Swiss Army knife of the energy transition because it can do anything. And they don't realize just how apt that analogy is. It really is like a Swiss Army knife, handy in a pinch, but it's the wrong tool for just about every energy related job you could put it to. People are pressing it into applications like heating and transport, which we'll talk about in detail, that it's really quite unsuited towards. And they're also thinking about using it as a way to basically be a very inefficient grid storage battery. And those applications, when one understands the motivations of the people involved, it becomes clearer as to what's really going on. It's certainly not something that a thermodynamicist would argue for. And a lot of this is kind of wishful statements about, hope for the future. And hope is fine, but you must hold your hope within the limits of physics, right? Within the limits of thermodynamics. And if your hope is that someone's going to set aside the law of conservation of energy to your benefit or to the benefit of your idea, you probably have to think of something else. The reality of hydrogen is that it's a decarbonization problem the size of the entire aviation industry. It generates at least 900 million tons of CO2 emissions per year. We make 120 million tons of hydrogen per year. So by the time you have the syngas and so on figured in, it's probably north of that 900 million tons of CO2 emissions per year. And basically all of it, 99-ish% of it, is made from fossils without carbon capture, which makes it actually more emissive when used as a fuel than if you just burned gas itself. A lot of it is made from petroleum and used in petroleum refining, and that those two sources and uses almost balance. A little bit is made by as a byproduct of making things like bleach and sodium hydroxide in the chlor-alkali process. And some of that comes from renewable or nuclear electricity. But by and large, everything else is made from fossils without carbon capture. The other thing that's really important is that almost all of it is made where it's used. We don't move hydrogen around very much at all. The largest uses, and you see the uses have grown enormously over the past 20 or 30 years, but the majority uses here are for things like ammonia, which is the base of the whole nitrogen chemicals industry and literally feeding about half the humans and their food animals on Earth. Another big bar there is the desulfurization of fossils before we burn them, which of course we won't be doing in the future. We'll be desulfurizing just that portion of petroleum that we use to make chemicals or plastics, and then the portion that we're burning right now, which is basically 75 to 85% of every barrel, we just simply won't be producing and won't be desulfurizing. And then there's a number of other uses. There are things like the direct reduction of iron ore to iron metal, That's currently done with synthesis gas mixtures. There's the manufacture of methanol and a bunch of other uses. In a decarbonized future, we're going to need about 90 million tons because about 30 of the 40 we use in petroleum is going away, as I mentioned, plus whatever new uses we will need. So it's instructive to think about what hydrogen is by thinking about how we make it. So the first thing we would do is we would start with an energy source, methane as an example, and natural gas or electricity. And the first conclusion we can draw already is that hydrogen is a fuel made from another fuel or energy source. It's basically, yeah, it's a fuel because when you burn it, you get heat, but it's really just an energy carrier. It's a vector. Now we feed it to a machine like a steam methane reformer or an electrolyzer, and we use that to make hydrogen. And in so doing, maybe we'll generate some CO2 emissions. For instance, if we start with methane. But in either case, we'll also throw away about 30% of the energy contained in the feedstock. And we'll also add a bunch of equipment, capital costs. We have to buy, a methane reformer or an electrolyzer, and we have to pay for that. Now, automatically, we can conclude that hydrogen can never be cheaper than the methane or the electricity that it's made from. That just stands to reason, right? So, okay, we're left with 70% of the original energy that we started with now in the form of hydrogen's lower heating value. Well, what can we do with it? Well, one pathway is that we can compress it or liquefy it or make it into something else. And then we can feed that material to a fuel cell or a turbine, and we'll have electricity or mechanical energy out the other end. And so that's basically kind of the battery pathway, if you will, using hydrogen as immediate as a battery. And you can see the losses there are quite substantial. So we lose 30% of the energy on making hydrogen, then we lose between 10 and 40% more making it into something else or compressing it for storage. And then we lose another 40 to 50% feeding into a fuel cell or a turbine. And the very best case, when you take the most optimistic figures there and multiply them by one another, you get 37% efficiency, of your source energy turning into the energy that you need at the end. And the answer there is, conclusion is really clear that hydrogen is a really terrible battery. So the other thing we could do instead is we could burn it, and we get some losses which depend on how efficiently we're burning it and for what purpose, making high or low temperature heat, and we'll make heat. And then best case, we're talking about a 63% cycle efficiency, which is considerably better, but it's still not great, especially relative to, for instance, feeding electricity to a heat pump and getting 2.5 to 3 joules of energy for every joule of electricity that we feed. So we can conclude that hydrogen is also a very lossy heat source and not something we're going to reach for by choice, but rather something we might reach for out of desperation. The big question is, how do we solve the problem of hydrogen itself? Because as I mentioned, it is a decarbonization problem that we must solve. Well, if we just do simple math, we use a very optimistic 50 kilowatt hours per kilogram for electrical generation of hydrogen from water, and we have to replace 90 million tons a year of this stuff, we come up with needing 4,500 terawatt hours of electricity. And if we had electricity to feed those electrolyzers 24/7, that would be 513 gigawatts of electrolyzers running at 100% capacity factor. And you can see that, in the world in 2019, we only made 2,100 terawatt hours of wind and solar on the entire Earth. Now that's growing by leaps and bounds year over year, but still we need twice as much energy and then some as we made in 2019 from wind and solar in order to just replace the hydrogen that we're going to need post decarbonization. So this is a massive problem just to green the existing hydrogen supply. So it is a bit of a puzzle as to why people would be pitching the notion of using it in inefficient uses like heating or transport. The other thing that we can conclude is that there basically is no meaningful quantity of green hydrogen. This is hydrogen made by electrolysis of water using wind and solar on Earth right now, because almost all of that 2,100 terawatt hours is used for things other than running electrolyzers. The other thing is, of course, that wind and solar don't operate at those high capacity factors. So this 500 gigawatts of electrolyzers is actually closer to 1,500 gigawatts of electrolyzers in reality. And the cost of that is absolutely crushing. So the notion that we're going to have excess green hydrogen to waste in inefficient uses is a little premature, like say by decades and decades. Now, we might wonder what this might cost us. And if you do the math on that, take our 50 kilowatt hours per kilogram, which, by the way, is next to impossible to do to be that efficient. But if you were to do that and you had 3 cents per kilowatt hour electricity, you could make hydrogen for $1.50 a kilogram, but only if you found the electrolyzer lying in the ditch somewhere, if it was free. And in reality, we have to pay capital cost and other operating costs to run an electrolyzer and compressors and all those other things. So already this cost of $1.50 a kilogram, which is kind of the reference cost of wholesale black hydrogen made from natural gas with no carbon capture, is going to take some very cheap electricity and also some very cheap electrolyzers. The reality is electrolyzers right now are too expensive to make hydrogen part-time. You pretty much have to run them steady, which means you have to run them off of either hydroelectricity or grid electricity, in which case their carbon emissions associated with the fossil fuel portion of most grids becomes troublesome, and very soon we eliminate any benefit that we're going to get by trying to make the hydrogen using electricity. The other thing is that the electrolyzers themselves will mass produce them and they'll get cheaper, but their balance of plant, the rest of the stuff, it's tanks and pumps and stuff like that. It's things that we've made billions of already. And so there's no learning curve in terms of cost reductions to be had there. The only way we can make those cheaper per kilogram of hydrogen is to make the plants bigger and bigger. So instead of building a 100 megawatt electrolyzer, you build a gigawatt electrolyzer. Instead of building a gigawatt, you build 5 gigawatts on a single site, for instance. Ultimately, the problem here is that hydrogen itself is structurally expensive. It's really foolhardy to waste it as a fuel. We really shouldn't do that unless we can't figure out something else to do. So in terms of the conclusions, if you want to make cheap green electricity, you need high capacity factors. And that basically means that you need hybrids of wind and sun that happen only in a few places in the world, like Western Australia, the west coast of Africa, Chile, places like that. You need giant scale projects, gigawatts and gigawatts, in order to drive the cost per kilogram down low enough. And then you need to also wait until electrolyzers get cheaper. But that means in the meantime, somebody, meaning us through our tax dollars, have to pay for expensive hydrogen made by expensive electrolyzers in order to get to that point where they're cheap enough. So we have to subsidize our way into cheap hydrogen one day, maybe if we're lucky. And the other problem is that the places where these high capacity factor wind solar hybrids are available also happen to be distant from anybody that needs electricity. So it sounds great to make hydrogen out of them, but then the problem becomes one of how do you move the hydrogen anywhere? Because hydrogen is big and bulky. It takes up a lot of space, even when it's compressed to very high pressures, or even when you make it into a liquid by cooling it to 24 degrees above absolute zero. So hydrogen distribution problems become the trouble, even when you can make it cheap. Well, of course, in Canada, we have the option, I guess, because we have, at least in theory, good geology for burying CO2, that we could, instead of making hydrogen by electrolysis, we could make hydrogen the good old-fashioned way by reforming natural gas and then capture the CO2 and bury it. So this is kind of a simplified model of a steam reformer. You basically take the gas that comes in and you split it so that about 30% of the gas comes off the feed and goes right into a big furnace that heats up the tubes of the steam reformer. And then all of that CO2 comes out through the stack of the steam reformer as post-combustion CO2, which is hard to capture. And then the other 70% gets fed through the reformer and gets turned into hydrogen. And then you have to purify that. So some of the resulting syngas comes back mixed with hydrogen, and it has to be burned. So what comes out here is about half, a little bit less than half of the CO2. And the other half of the CO2 comes out of the gas purification train. This stuff's easy to capture. This stuff is economically next to impossible to capture. And the capture costs a fortune because you need more energy, electricity and heat in order to run the capture equipment. And so we have a project that does exactly this. It takes a steam methane reformer and it captures about 80% of this easy portion, which is about 45% of the total, and buries it to the tune of 1 million tons of CO2 per year. It's called Shell Quest. It's in Alberta. It's on the Scotford Upgrader. But by the time you take into account the extra natural gas that has to be burned to make heat and electricity in order to run the compressors and the capture equipment, the net capture drops from 45% to 35%. The other problem is that we've got methane leakage, both here at the front end and then associated with making this other energy here. And if you take that into account, it drops the CO2 equivalent capture from 35% to 21%. By the way, this plant cost $1 billion of Canadian taxpayers' money, both Alberta and federal money, and it costs $50 million a year to run. And the most recent capture cost for 2021 was about $145 per ton of CO2 emissions averted. So that forgets about the equivalent, the methane emissions, that just ignores those and pretends that they're not there. It's costing $145 a ton to bury, just to capture and bury that little bit of CO2, the easy bit. So really what you're getting here is blackish blue and bruised colored hydrogen at best. And if you wanted to fix that, you need to abandon the steam methane reformer entirely and replace it with a machine called an autothermal reformer. And what it does is it actually uses more electricity to make pure oxygen. It reforms the natural gas with steam and pure oxygen, doing some partial combustion inside the device, and then all the CO2 comes out here. There's no post-combustion CO2, and it makes capture easier. But the trouble with doing this is that it's expensive and it's not as efficient as steam reforming. And the big problem is doing this inefficiently and capturing less CO2 makes you more money if you're still considered to be green enough. Or blue enough, if you will. So this is a fundamentally difficult to trust situation. You need really good regulatory controls to make sure that the people that are making the hydrogen by this method were actually capturing and burying what they said they were, and that these leakages weren't high enough to cause big problems. And honestly, you know, trust us is not going to be good enough here. You need really good regulatory controls. So for a moment, it's worth considering when we talk about hydrogen for transport, what it's competing against in the modern world. It's not competing against gasoline engines. I mean, the gasoline engine was a great thing because gasoline was very effective, not very efficient, but very effective. It's a liquid, it's very easy to store and transport and so on. So the thing we're really talking about competing against is the electric vehicle, which I think a lot of people that are here tonight are probably already big fans of. I certainly am, enough to do conversions, as I mentioned. When you look at the various losses in the chain from the energy source, from the power plant all the way to the output of the motor shaft, taking a 6% grid loss, which is kind of average for North America, it's a lot lower where I live in Toronto, it's closer to 3%. Charging loss of about 7%, and then motor controller and battery loss of about 10. Motor and controller loss of 10 and battery loss of about 6, which is honestly is a little high. Charger plus battery loss of 7 plus 6 is a little high. It's probably a little lower than that. Certainly wasn't my conversion. When you multiply all those out, you get that, you know, for 100 joules that you put in from the wall, you get about 74 joules back out of your motor, which is awesome. And even if we were to feed a natural gas power plant at the front end with 60% efficiency, which can be achieved, and put that in the front, we're still at 42% cycle efficiency. That's assuming that it's 100% gas fired. And of course, no grid, especially Canada, is 100% gas fired. We have some renewable or low emissions content in every grid in the country, with the possible exception, I guess, of Alberta and Saskatchewan. And of course, in the future, we're going to be making this electricity from renewable resources. So it's going to be pretty clean and pretty low in CO2 emissions, delivering work out the motor shaft very efficiently. What's not to like here? Now, when we look at a fuel cell vehicle, we put the same grid loss in, and then we put in an electrolytic loss of 40%, so an efficiency of 60% on the lower heating value basis. And then we have to compress the hydrogen to store it, and that's about a 90% efficiency or a 10% loss. And then we have an electric vehicle, except that it has a fuel cell, and the fuel cell loses another 40 to 50% of the energy that we feed it in the form of hydrogen's lower heating value. And that now we have an electric vehicle with its motor and controller loss the same as last time. And on the same basis as before, we're talking about, instead of 74% efficient, we're talking about 27% efficient. That's a rather dramatic difference. And, people will automatically say, well, what does it matter? It makes no difference. Electricity is going to be super cheap, and 3 times nothing is still nothing. What do you care if it's inefficient? And the answer is that anytime something's inefficient, that inefficiency is acting as a multiplier on all the impacts associated with the front end. And wind and solar are great, but they're not emission free. There are emissions associated with building, making the materials, installing and operating those energy sources. And there are greenhouse gases associated with every part of that life cycle to some degree. And tripling those there has to be a good reason to do that. And really, what's the reason here? It's maybe faster refueling and possibly modestly larger range, but even that's arguable. So certainly the faster refueling is it's the only solid thing. You can fill up a Toyota Mirai under 5 minutes if there's a hydrogen station along your route. So is 3 times as much energy use worth faster refueling? Is that really a value proposition that we can find honestly to be acceptable? I don't think that it is, but others are free to differ with their own money. When you do a comparison of 2 cars, the Toyota Mirai and the Mark I, and the Tesla Model 3 long range version, basically the comparison is stark. The hydrogen car is heavier, it costs more, it uses 3.2 times as much energy from source and costs over 5 times as much per mile driven. So really there isn't any win here for hydrogen. And honestly, even the hydrogen community has more or less decided that hydrogen for cars and light trucks is not going to be a thing. So people say, okay, great, hydrogen cars are dead. What about trucks? Because the hydrogen advocates aren't going to just give up. They're going to retreat. They're not going to just say, well, it's useless for transport, let's give up. They start talking about heavy trucks, Class 8 trucks, tractor trailers. And they claim that, trucks are hard to electrify. And it begs the question, why are they saying that? Because trucks are really kind of big cars that are owned by people that understand total cost of ownership better than car owners do. So one of the things that you hear is, well, the battery's too heavy, and that's going to reduce the maximum gross vehicle weight. It's going to reduce the amount of load that you can carry within the limits of the maximum gross vehicle weight that is permitted on the road without damaging the road. And so that will make freight more expensive. And the reality is that about 75% of freight loads are determined by the maximum volume of the vehicle or floor space in the trailer, not by maximum gross vehicle weight. And of the 25% that are limited by maximum gross vehicle weight, a lot of those loads are loads of fossil fuels that we're just not going to be shipping in the future. So honestly, an awful lot of truck freight can be electrified by virtue of battery electric trucks. The other thing is that for the truly long distance, and especially the remote and rural transport situations where electric is not going to work well for us, like resupplying northern communities across ice roads in the winter, hydrogen doesn't suit those needs either, because hydrogen logistics are terrible. Hydrogen distribution and dispensing are both very expensive. And if instead of distributing hydrogen, you want to distribute electricity and then make hydrogen locally in tiny electrolyzers all over the place, that makes each kilogram of hydrogen very expensive. So it also makes the grid problem harder to solve, because now you're transmitting 3 times as much energy as if you just use the electricity to charge batteries. So honestly, for trucking, it's not looking good. The other problem is that we get people, you know, they'll show you this picture like from the promotional materials of this company, Nikola. They show this nice little pump, right, that we're used to seeing. We're used to seeing a pump and, you know, a hose, and we can connect that up to the vehicle. But it's like in The Wizard of Oz, you know, the real business is hiding behind the curtain here. It's hiding behind this fence. This picture in the lower right is the equipment that it took for Toyota to keep one hydrogen engine vehicle, not a fuel cell vehicle, on the racetrack for 24 hours. And that's a lot of expensive kit. It's not only a bunch of hydrogen Class 8 tube trailers because they didn't want to have high pressure compression there, but there's also a dispensing compressor and chiller inside this thing that are quite substantial. And then over here are the diesel generators that run all of this kit. So there's a lot of stuff here that somebody's got to pay for. It's not just a little pump. So, you know, hydrogen is possible, but without the scale of cars to drive the learning curve on fuel cells are going to be too expensive, in my opinion. EV trucks are coming, and they will offer much lower total cost of ownership, and fleet owners really appreciate that. And truly long distance transport can't use hydrogen due to fuel logistics. And so where I think this is going is we're going to have EV trucks, and we'll use biofuels for the rest, biofueled engines for the rest, or just fossils, honestly, for the rest. Because if those emissions are generated at a small fraction of the total, and they're generated almost entirely in remote places where very few people live, and there are few people to be breathing in the exhaust, it's really not such a huge problem to imagine that biofuels will be sufficient to handle that balance. Aircraft, well, I won't trouble you in the interest of time, but my colleague at the Hydrogen Science Coalition, Bernard van Dijk, is a retired aeronautics engineer in the Netherlands, and he can explain to you with very nice infographics and presentations of the innumerable ways in which hydrogen is a poor choice for aircraft. Its energy density per unit volume is the deal killer for the most part there, just like it is in many other applications. And shipping, honestly, a hydrogen-derived fuel might be one of the possibilities there, something like methanol. But the real issue is that the operating cost of ships per ton mile of freight that they move is about 40 to 60% fuel cost right now, even burning the cheapest fossils that they can burn. So honestly, I think shipping is going to be the last vestige of transport to decarbonize. You could make hydrogen into a fuel like methanol, or even things like jet fuel type materials through this process called Fischer-Tropsch. And these processes are called, you know, power to liquids or e-fuels processes. And what they really are is attempts to contend with the difficult properties of hydrogen, its low energy density per unit volume, for instance, by spending even more of its energy in order to make it more effective, you know, to make it into a liquid that we can transport and store more easily. And look at these cycle efficiencies. You know, I was figuring 74%. Well, Transport and Environment, who came up with this original figure here, they were a little bit more optimistic, and they said 77% for an EV. And I was at 27% for a fuel cell. They're more optimistic at 33%. But they were really kind of out to lunch here with their figures for the e-fuels. And I have personal experience with this from past work experience. By the time you're down through all of this, you know, making hydrogen and converting all of this hydrogen energy into fuel energy, and then putting it through an engine, you're down to between 7 and 11% on a cycle efficiency basis. So buy 10 kilowatt hours, get one back, plus buying a whole bunch of expensive e-fuels manufacturing kit. Only Porsche owners are going to be able to afford to do this. The rest of us don't have to worry about it. It's just not within our price range. Lastly, I'll talk briefly about heating. We have this idea on our heads for the past 1,000 years or 10,000 years that anytime that we need to heat something up, we need to, set fire to something, we need to burn it. And since we can't burn fossils anymore, the problem is what else can we burn aside from fossils? And hence hydrogen to the rescue, right? Because when you burn it, you don't make any CO2. You do make nitrogen oxides, though, if you burn it in air, except when you burn it over a catalyst like in a fuel cell. So that's something to keep in mind. You do make NOx and you make lots of it because hydrogen burns hotter than other fuels. The reality about hydrogen as a replacement for natural gas is that blending 20% hydrogen into natural gas sounds like a lot, but in reality, it's only 7% by energy content. Hydrogen is really a diluent. It's like adding water to gasoline almost. And your next step isn't going from 20% to 30 and then 30 to 40 and so on. Your next step really from 20% is 100%. And unfortunately, when you do that, you end up with all kinds of problems. You need to replace every end user device, every burner, every boiler, every cooktop, every gas burning device would have to change because you can't burn them in the same device that would burn natural gas. It takes 3 times as much energy to compress hydrogen as it does to compress the same amount of energy worth of natural gas. So you need bigger compressors and more powerful ones. You need to change the piping of the transmission infrastructure because it's made out of the wrong materials that get brittle and fatigue and fail prematurely when they handle hydrogen. And the end result is, hydrogen, whether blue or green, is too expensive to burn as a fuel. It just doesn't make sense to try to convert the gas network to run on pure hydrogen. So it's really very difficult to justify, especially when you compare it against using electricity to run heat pumps instead of using that electricity to make hydrogen and feed that to the gas network. So this is the famous, a version of the famous Liebreich's ladder, which shows a list of hydrogen potential applications and their alternatives. And as you go down the ladder, the uses get more and more ridiculous and less likely. So you see the top row here, these ones that are kind of reddy color, they're fertilizer, hydrogenation, desulfurizing and hydrocracking petroleum, hydrogen use in chemicals, and to some degree methanol. And in fact, even iron reduction rather than steel production, those are all no regret uses for hydrogen. They're really replacing black hydrogen with green hydrogen. And the rest of them are all, they have competitors, and they're questionable. And as we get down here, cars, 2- and 3-wheelers, hydrogen bicycles, trains, etc., heating, all of those applications are low merit order uses, and they would really be a waste of the source energy that we used to produce hydrogen from them. Here's an illustration of the 5 principles of this Hydrogen Science Coalition that I helped to co-found. And as stated there, they're very straightforward. We shouldn't give credence to blue hydrogen. Really, green hydrogen is the only thing that's going to be adequately clean to be a real decarbonization strategy. We shouldn't let hydrogen delay electrification applications, and we certainly shouldn't let hydrogen gobble up renewable electricity that could be used to decarbonize our grid instead. We shouldn't think of hydrogen as an export commodity. We should make and use it locally to the extent that we can. And if we have to make it in places with high capacity factor renewables, we should make something there that we then export to the world. So I see, for instance, Chile and Australia cornering the market on ammonia production for making fertilizers, for instance. We should decarbonize those durable uses of black hydrogen first, like ammonia production, and we should just forget about hydrogen blending and replacing the natural gas. Replacing natural gas with hydrogen. You just forget about doing that. It's not a high merit order use for the gas. And, another way to put it is my little Drake meme here. Hydrogen is a fuel? No way. Green hydrogen to replace black hydrogen, that's the thing to do. There are a few other uses like increasing biofuels yields. Maybe if we're rich and desperate to make some e-fuels, but honestly, that's like decades from now. And maybe some uses in very high temperature heating, but that's pretty much it. And with that, I'll leave you with just one caution before we get into the questions. And that is that in the interest of time, I've had to make a lot of assertions, as if they were fact. And I encourage you to never do that. Never just take people on their word about those things. Everything that I've said here tonight is backed up in my articles, which you can find, for instance, on my blog at spitfireresearch.com and on my LinkedIn profile, which you can also find there. I've got about 30 articles there, and they're quite accessible. They're not written like technical papers, but they give you all the references and the detail as to why I've come to the conclusions that I have. And I also edit my articles as my opinion changes, as people change my mind and as circumstances change. And that's the most important thing that we should be doing, is we should be focusing on getting the thing right, getting decarbonization right, rather than on being right ourselves. And with that, I'll leave the floor open to questions.
Thanks very much, Paul. And I am going to call on Jason now to take us through some of the questions. Jason?
Thank you, Tim. Thank you, Paul. We'll start with a nice wide open one. Why are fossil fuel companies, especially fracked gas companies, promoting hydrogen so much?
Oh, yeah. Well, it's really straightforward. If you own a gas network, or you own natural gas leases or natural gas production platforms or wells or the like, in a decarbonized future, you're done. You're toast. You're out of business. Your share value is based on assets that are really liabilities post decarbonization. So unless you can find something else to sell in those pipes, or another way that you can use that gas to supply people with energy, you're out of business. So of course you're going to push hydrogen hard. I mean, there's no question about it. And then of course there's the fossil fuel industry that loves hydrogen because it either delays, the way that Liebreich puts it, is that it's a win-win for the fossil fuel industry. Hydrogen either delays decarbonization, or it gets them into the business of blue hydrogen production, burying the CO2, and either way is a win for them. But the renewables guys are in the same boat. They want to make big wind and solar projects, and sometimes they can't get the grid built fast enough, because they don't have control over the grid. And so they think, I could build a great big project here, but I can't sell electricity because the grid is so old and recalcitrant. So I need to make something else. So why not hydrogen? Oh, crap. Now, how do I get the hydrogen to users? Well, we'll sell it for heating. So yeah, that's really what's going on here. It's propping up, it's the sunk cost fallacy and propping up existing value propositions for the fossil fuel industry, really, as well as the renewables industry that's kind of in a growing pains situation, can't get their product to market.
Thank you. Next one is, there is much in the news about Canada providing vast quantities of hydrogen to Europe in the coming years. What's this all about?
Oh, sure. Okay, so the Europeans are, of course, desperate to shift away from their dependence on Russian gas. That's a very desirable thing, and we should try to help them out as much as we can. But of course, we decided long ago, on the basis of average values for natural gas, and of course, the future being a decarbonized future, that we weren't going to build LNG terminals on the east coast of Canada. And now people want to revive those zombie projects. They're dead, but they're not really dead, but they'll never really be alive either. They want to revive those projects, but of course, if someone says, well, if we build this LNG terminal, that means that we're not going to meet our greenhouse gas emission targets. We're building new fossil fuel infrastructure, and we can't do that anymore. So what people will do, including our prime minister, he said this at the G7, is, okay, we might build some LNG terminals on the East Coast, but don't worry, we'll convert them to hydrogen later. And that is just nonsense. There's no way that you can convert an LNG terminal to carry liquid hydrogen. And honestly, shipping liquid hydrogen over transoceanic distances, that's not going to be a thing either. It's just crazy. If they're going to ship anything, they're going to ship ammonia. And if you make ammonia, you're going to make it where you make the hydrogen, which you're going to make where you make the electricity. And then you're going to ship the ammonia from there. You're not going to bother with an LNG terminal. So a lot of these East Coast projects, the problem that they're going to have is that if you took the same equipment and you put it in Australia or Chile instead of in Newfoundland, the same amount of investment makes twice as much hydrogen per year. So the economics in Canada are not good. Canada's not going to be a low-cost producer of green hydrogen. We just don't have those combined wind-sun hybrids that make the cheap hydrogen. So, of course, in Canada, the thought is, well, we'll make blue hydrogen and then sell it. But that, the distribution problems and the fact that the natural gas grid can't handle that pure hydrogen basically makes that a non-starter too. So Canada's out of this, honestly, other than, kind of having the fossil fuel industry here jerk our chain around about heating and transport applications locally or within Canada. This whole export thing, that's just to try to get people excited about it. I don't see it really honestly happening.
And you touched on something there that I'm surprised you didn't mention earlier. To the best of my knowledge, two of the problems with hydrogen are storage and just it leaks. You have to keep it cold, you have to keep it compressed, and it gets out of anything.
It doesn't just get out. So I used to design, for a living, I designed and built pilot plants. So these are small chemical plants that are used to test new ideas before they get commercialized. And I'm still involved in that industry, just not designing and building them directly myself anymore. And when we designed and built pilot equipment that used hydrogen, sometimes we'd have to measure the level of products inside vessels that were full of hydrogen. And what would happen is the level measurement devices, they had these thin diaphragms made out of stainless steel. Hydrogen would permeate right through the diaphragms, not through holes, but through the intact stainless steel of the diaphragms and get to the other side and mess up the measurement. And so in order to make those units last longer, we used to plate them with gold. And even gold plating wasn't enough. So honestly, the notion of keeping this very sneaky, very leaky gas around, or an ultra cryogenic liquid where, in a truck-sized tank, you lose 1% of it per day to boil off, is just nuts. It's just not practical. People are pushing the idea of it without getting into the details, and the devil's in the details there. He's waving his pitchfork at you.
Here's one that's a little bit of a tangent. Elon Musk has mentioned using electrically produced methane as a green combustible for rocket propulsion. Is methane any less insidious?
Yeah, on Mars. He's talking about doing that on Mars. He's not talking about doing that here on Earth. The thing, and honestly, this whole Mars thing, we have to focus on the planet we live on. That's existentially important to us. So the whole Mars thing really is not, it's a distraction as far as I'm concerned. But let's say you had CO2 and you had electricity and water and you wanted to run thermodynamics backwards and make something to burn. The thing to make isn't methane. Because in order to make methane, you have to unburn CO2 all the way to CH4. So you have to produce, two waters. And instead, what you could do is you could produce one water and make methanol. And methanol is a liquid at room temperature. So if we're going to make something out of water and CO2 and electricity, it's going to be methanol. It's not going to be methane. The other one that people are pushing, and it horrifies me as a chemical engineer who understands chemical risk management very well, is the notion of burning ammonia or using ammonia as a ship's fuel. That absolutely terrifies me. It fails the very first principle of safety and design, which is don't use a toxic gas as a fuel. That's just nuts. So yeah, it terrifies me that people are thinking about that. They would be thinking about using it because it's easier to make ammonia because there's nitrogen in the air everywhere on Earth. Whereas if you want to make green methanol, you have to have some green CO2, you know, from fermentation or from a biological source. Also, where you have your excess electricity to make your hydrogen. So it's harder to make methanol and make money at it, whereas making ammonia is more possible. But burning ammonia is horrifying. It makes NOx like crazy. It's a toxic gas. It's extremely toxic in an aquatic environment. You know, 1 ppm in an aquatic environment is death to most aquatic organisms. So it's really bad news, a really bad idea.
Okay, back to the car industry. Why do you think Toyota chased the hydrogen solution for so long?
Well, I mean, it calls for speculation, of course, but I think Toyota did a couple things. One is Toyota is a very, you know, big company in Japan and very messed up in Japanese politics. Japan is one of those countries, South Korea is another, that is going to come off out of decarbonization much worse off than they are today. They have large populations, they're very energy hungry, and they're 100% dependent on imports of energy from elsewhere. And they're not good friends with their nearest land neighbors. So, you know, importing electricity over a high voltage DC cable, like our American neighbors do from us in Quebec and Newfoundland, is not something that's going to be very appealing to Japan or South Korea. So they want to import something by ship just like they do now. So they're casting around for hydrogen for those reasons. The other is that Toyota had some early experience with with hybrids that you would think would position them very well. But they made some pretty lousy, pretty expensive plug-in hybrids. And those didn't sell very well, and they kind of convinced themselves, see, electric cars are just no good. And, you know, once the senior management at a company like that make decisions, it's very difficult for them to change course without admitting, you know, without losing face. So yeah, I see that as very unfortunate, because I mean, I own 2 Priuses, a Prius C and a Prius base model, and I think they're great cars. And it's really too bad to see Toyota going away of all flesh. But I think, honestly, they're, you know, at this point, it's going to be very difficult for them to pivot to battery electric vehicles and survive. And sticking with hydrogen, I mean, it's a dead end for sure.
Okay, here's one about the various hydrogens. Perhaps one of the most concerning aspects of green hydrogen is that it may create a demand for hydrogen that will justify and generate a demand for gray and blue hydrogen.
Yeah.
What do you think?
Oh, no, I totally agree with that. I think what'll happen is that, you know, countries like Japan, as an example, are talking about importing hydrogen from Australia, and they're really kind of not worrying all that much about the color, because then the emissions get generated at the source, right? So they actually did a project where they, you know, the Australians gasified coal to make hydrogen, which people in China do a lot of as well. And they claim they're going to bury the CO2 later, but not now. It's very unlikely they'll ever bury the CO2. And then they liquefied it, and you lose 30% of the energy in the hydrogen on liquefaction. But that energy is expended as electricity, not as heat. So you have very little left at the other end. And then, of course, they ship it to Japan. And very little of it actually gets there, because it's quite a long sea journey, and a lot of it evaporates or is burned in the engine of the vessel. So honestly, there's a lot of worry that people will say, well, green hydrogen's coming, don't worry, it's coming one day, but in the meantime we need hydrogen, so let's just make it the old-fashioned way. And that's actually going to drive emissions up, not down. So bad idea. Okay, the big thing that I'm worried about, though, is that it takes the pressure off fixing the grid and getting renewable electricity in larger quantities to users, right? Like, oh, we don't need to worry about that grid stuff. Let's just make hydrogen with this excess wind and solar. And, you know, there's a lot of talk about making it with excess wind and solar. You can't afford to make it with just excess wind and solar, you know, because the electrolyzers are too expensive. You can't run them 5% of the time and make money. There's no way.
Thank you.
Go ahead.
Tim?
One more. We got to do
One
one more.
more?
Just make. We'll have to make it quick, but we
Yeah,
got to do
no
Okay,
worries.
this one should be quick. I'm going to paraphrase because I think you've answered some of this already, but for the user or driver, do you see any benefits of a hydrogen-powered car?
Familiarity. That's pretty much it. I mean, you look at that comparison that I did between the Mirai and the Tesla Model 3. I mean, it accelerates half as fast. It's 200 or 300 pounds heavier. You know, it costs more. It costs more to drive it. It accelerates half as quickly. But I guess it's familiar. I guess you're pulling up to a gas. I'm not romantic about pulling up to gas stations. That was one of the best things about building my EV was that I did not, the only time I went to a gas station was for coffee. I love charging at home, and I charge to work too, just off a landscaping outlet at level 1. I didn't need any more, and my commute was longer than most people's. I had a 122-kilometer round trip commute, and I was doing it in that tiny little car with an 18.5 kilowatt hour battery pack. And that was no problem. The only worry I had was if I got fired first thing in the morning, I'd have to wait a couple hours before I could go home, with my stuff in a box. So, it really was never a problem. The distance from work to home was the same within 5 kilometers, even with road blockages or whatever every day. It was never an issue. And that's most people's driving most of the time, honestly, stuff like that.
Yeah. Yeah, it's an interesting fact that folks who are still driving gas cars can't. It's really hard to imagine what it's like to drive an EV. It's such a shift in the paradigm of what people are accustomed to, that until they do it, they don't even understand their own driving habits until they do it, and then it becomes they become fearless and they realize, oh my gosh. This is just fine.
And people that buy plug-in hybrids, largely the next car that they buy is a full EV.
Yeah, it's the gateway.
Because they realized that they were carrying around a big internal combustion engine safety blanket that they didn't need.
Yeah, and they could have driven a lot further without all that weight. Paul, thanks so much for this. This is really very interesting. It's very enlightening. I learned a great deal. I hope those listening did as well. I'm sure there was learning going on for everybody. And Jason, thanks again. Really appreciate. There's some. I was looking at the questions. I think we could probably go on for another half hour, but we do have to call it quits.
Well, do feel free to reach out to me, via my LinkedIn profile or via spitfireresearch.com. And if you have any questions, don't hesitate. If I'm too busy, I won't answer, but there's lots of resources there and other podcasts and things that I've done that may help.
Great stuff, Paul. I'm going to put a few of your links in the notes on the recording on our YouTube channel. And so people will be able to reach out to you and connect that way as well.
That'd be great.
Thanks, Paul. Thanks a lot.
Cheers.
So on our next episode of Canada Talks Electric Cars, we're going to take a look at car dealerships across the country, and specifically at the long wait times and narrow inventory that we see for EVs. Jeff Turner, who is the Director of Mobility for Dunsky Energy, will be here to present some recent findings that they've done concerning the availability of zero-emission vehicles right across Canada. And we'll look at the different provinces and note the differences there. So remember to mark that date. It's going to be Tuesday, April 4th, always at 7:30 Eastern Standard Time. So thank you all for joining us for today's episode. If you happen to be watching this episode recorded on our YouTube channel, please do take just a moment to subscribe and at least give us a like, because that does help us greatly. It moves us up and makes us easier to find on YouTube. So from all of us at Electric Vehicle Society, and until next time, stay well. This will conclude today's webinar.